Okay, greetings everybody. How are you doing? Good. Good? All right, very enthusiastic. What are you enthusiastic about?
It's a great day, homework's all done, it's almost the weekend.
Okay, wow. That sounds good. That sounds good. So I'm very grateful for the opportunity that we have to meet again. And this meeting is our last one before exam number 1, okay, which is on Tuesday. Any questions administratively? Yes, Daniel, yes.
No. Do we need on the formula sheets to have all of the conversion factors, or it will be given, I don't know, pound to kilograms, Pascal, to ATM?
So I think if you look at the previous exams, you have a pretty good idea of what is expected. On the exams, I don't typically say, hey, this is in foot-pounds, and now I want an answer in millimeters, or radians or something, you know? Well, radians would be fine, yes, sorry. But yes, yeah, you want to, reasonably well, right? At this point, if I have a meter, right, and I have a megameter, which I don't use in this class, right? We know it's 10 to the 6, right? A Pascal, megapascal, gigapascal, 10 to the 9, right? The biggest thing for me personally that I'll mess up probably before the end of the semester on an exam is I will write down a diameter in the problem, and then I'll use diameter instead of radius, okay? So that's not really a units thing, that's just I gotta divide by 2 thing, okay? All right, so I think we're pretty reasonable if you look at the previous exams. Yes? That's correct. So this session was, I think, in the past on exam 1s, but we moved up our exam date to accommodate the other class. And so this session is not going to be on the exam. That said, this session is long, is a doozy, okay? So you know, what would I do? At least work on this a little bit. So this is what we're gonna do. I'm not gonna spend too much time presenting stuff, shall we say, today, right? Because maybe people want to talk about exam questions or previous homework problems or stuff that, you know, might be on the exam on Tuesday. That said, I would probably start this stuff, okay? Because it will give you a little bit better idea of how you might use the torsion formula, which is fair game, okay? Because that's what we cover on Tuesday. So you have a little bit, you know, an idea, and that way when you finish your exam, you're so happy you finished your exam on Tuesday, you don't have 7 problems to do before Thursday, okay? So, yes?
I'm sure this is common knowledge, but I'm not aware. How is the exam administered? Is it on like laptops in the classroom, or is it on paper?
It'll be on paper.
Okay.
Yeah. So you can see the previous exams. 2020, right, that was obviously, well, not obviously, but that exam was online. But then after that, the other one was 2022, and the summer and last semester were paper. Yeah.
And then also, we only get 1 formula sheet.
Mm-hmm. Yeah.
Are there any like conditions to that? Like
Yes. And it must be handwritten. No copy and pasted figures, but you can write whatever you want. So if there's an exciting example problem, go ahead, write it down. So yeah, write whatever you want. Yes?
Will it be the same format?
I expect that the introductory paragraph will be verbatim. Okay, yeah. Other questions? Okay, so session 10, more torsion, okay? If you recall in our last meeting, we discussed shear strain, shear stress, how they're related to each other, and we'll talk a little bit more about how they're even more deeply related to each other. And we also discussed how we can go about thinking about local shear strain along or at some location from the center axis of a shaft, right? So what we were doing, right, is, well, a couple things. We were, in the end, this is kind of the major takeaway, right, that we could come out with a formula that relates an applied torque to the maximum shear stress. And that maximum shear stress is going to be along the outer surface or just below the outer surface, okay, of a twisted shaft, right? And I mean, I don't know if maybe I didn't make this as clear as I should have, but we're talking about shafts, rods, right? And this class is typically going to be something that's circular, okay? We can do square and rectangle, but yeah, for the most part, we're going to be dealing with something that's circular or hollow even, okay? So you have an outer radius and an inner radius. And I mean, I guess that brings up another point. The polar moment of area is a pretty big concept that you want to have down even for exam 1, okay? And if, and I don't think I emphasized this enough, this equation right here, this tau equals T torque times rho times over J, okay? This J, right, so the rho is not the C, right? Assuming like I'm like if this were solid, right, and I'm at some radius from the center, okay, then I'm going to use this second formula right here, the second version of the torsion formula. And what's important to remember, okay, is that yes, the distance I'm using in the numerator might be like half the radius or something like that, or a third, or 5/8, whatever it is. But that J does not use rho. That J is using the C, the radius of the entire structure. Okay? So just keep that in mind. And we do use, and that may be a little counterintuitive. You're like, well, J is equal to integral of rho squared dA. Yes, but it goes from 0 to C. Okay? And then if you need a hollow, if you need a J for a hollow, well, you're like, okay, it's got to be less. There's not as much material there. Okay? Then I'm going to just subtract. I'm going to do the J of the outer one minus the J of the inner one. Okay? So I may not have emphasized that too much in our last meeting. And then what we did emphasize, though, quite a bit is what is d phi dz. All right, and that is essentially how much twist, right, do you have? And in this case, z is going along the z-axis is coming out of the middle of the cylinder. Okay, and what we're saying is that there's some essentially slope. That's all we're saying. There's some slope of this displacement. Okay, as you would move along z. All right, of this radial or this not radial, this angular displacement. Okay. So we can figure out what that strain is. That strain is going to be the same no matter where you are in the z direction, but it's very much dependent on how far you are from the center axis, right? And that comes out in the math. Right? That comes out in the rho d phi dz. Okay, so this is kind of, you could even say this is maybe the first review. If you're going backward for exam 1, make sure you have this stuff down and you understand it. Okay. I would not make you do the derivation. Okay, that's not really. It's not the style of the way we're doing this course. Okay, so okay, that's a really cool derivation. No, but can you, if you have one of these major formulas and you're required to do the integral of it, right? You should be able to do that. Okay, so I said we talk a little bit more about the material properties and the relationship to shear stress and shear strain. Okay, so we came up with these relationships. All right, let's back up. All right, this is the torsion formula. Okay, at a given radius from the center axis. this is Hooke's law, but now adapted to shear strain and shear stress. And we said, okay, I could take this equation and come up with a shear strain, either at a distance from the center or at the outer radius. Okay, and we said, just look, take this for what it is right now, that the shear modulus is equal to E over quantity 2 times 1 plus nu. I would give you this, don't worry, at least on this exam, maybe on the next exam, but I would give you this on this exam. Okay, and then we have the ability to think about these shear stresses as they relate to these shear strains. Okay, and we can put this in a matrix, or we can put this shear modulus in essentially an identity matrix. Okay, and look at a relationship between taus and gammas. All right. Is there a question? Yes.
Could you just say that it's like tau is G times gamma vector?
Yeah. Oh, that's what we're doing, right? I mean, if you want to use like index notation, right, you can say that tau subscript ij is equal to G times gamma ij, right? That's another way to write it. Okay. Good. Thanks, Mahadeva. All right. So now. So what we can also do, all right, is write out relationships now that go between the linear or axial strains and the shear strains and these parameters. Okay, so this gets a little bit wild, right? And you notice that, well, at least these quantities like epsilon x, right, is not going to depend on tau xy, right? Epsilon y is not going to depend on tau xz, okay? Because, you're doing this times, it's just the row times the column, right? And then you add up all the products. Okay, so you're adding up. So this is a nice way to kind of write out or figure out what the relationships are. So if you ever got like really confused, okay, you could have this big old matrix with a 1 over E, very important, okay, and you can calculate all these relationships, right? You remember that epsilon x is equal to 1 over E times quantity, the sigma x minus the nu times quantity sigma y plus sigma z, right? And that's all this is saying. It's just in a kind of a nice format. Taking the inverse of this matrix and writing it all out, now we can also go from the strains to the stresses. Okay. Do you need to write this on your formula sheet? Not really. Okay. But maybe, if you want to be like extra nerdy and you've got extra space, okay, I don't know if you could write it out. Okay. But it's for your good to know file, because someday you'll take another mechanics class and be like, oh yeah, I remember this. I could use matrices. I could use tensors. We don't do that in this class. All right. But if you take grad or you take advanced mechanics, you will. Okay. And then another thing I mentioned last time, just quickly, is that this is from session 1. Okay. That the supportable load scales with the diameter cubed or the area to the 3/2. And why is this? This is because of TC over J, or the maximum shear stress is going to be at the outer radius, right? And then J is dependent on C to the 4th, so it ends up being dependent on the inverse of C cubed. Okay. So we just validated what we said at the very beginning. Where is this going to fail? This is going to fail at the outer surface, because that's where the shear stress is highest. Okay, and we'll get into criteria for failure in the future. Okay. Any questions on this? Kind of a little bit of a review. Okay, another thing to keep in mind is J and I. What is I? That's the second moment of area, right? And this is the polar moment of area. Okay? What is I if you have a beam? We haven't really covered it that much yet. A little bit maybe. Okay. Well, the I is actually pi over 4, a circular beam, I should say. I is pi over 4 c to the 4th. J is pi over 2 c to the 4th. And how do I remember this? I comes before j, so I is less than j. All right, so I would be pi over 4 c to the 4th. And we'll do that more when we get into beam bending. Okay. Any questions? Yes, Kevin.
So I is in rectangular form of J?
No. So okay, so J is essentially in this class is a quantity that tells us how much there's going to be a resistance to twist. Like, so if J increases and I do the torque, then I'm going to have less shear stress, okay? I is so this is the polar moment of area, okay? Or sometimes referred to as a polar moment of inertia, but there's no mass there, so we can call it polar moment of area. The second moment of area, which is given by an I, is not the resistance to twist, it's the resistance to bending, okay? And they both involve looking at the cross-section, the geometry of the cross-section, okay? But that one is going to give us an idea of, okay, how much am I going to resist bending? So if I is larger, okay, then I'm going to have less stress, okay, less axial stress actually, okay, and we'll cover that. Good. All right. So you can go through the videos. I said I wasn't going to talk that long. All right, and then learn about angle of twist, or some of you will just look at the slide and be like, okay, I got it. Okay. By combining Hooke's law and the torsion formula, okay, and an expression for describing the geometry or the angle of twist, all right, or the rate of change, right? So we had this is a shear strain, gamma, rho d phi dz, right? And if what we're interested in, right, so d phi, recall that was the local, the small, right, infinitesimal amount of twist, essentially, right, of the angular displacement on a pizza. If you put all these together, you get this, and what do? You integrate. So we have an expression for d phi. We just integrate d phi from 0 to L. Okay. And of course, well, it's nice that d phi can be written in terms of dz because we're integrating from 0 to L. Okay. And you get this equation. This equation is extremely similar to bada bing, Pli, right? This one is for sure fair game for the exam. Okay, so that's how you figure out the displacement or the deformation of a bar under normal loading. And this one is how you figure out the angle of twist for an applied torque. All these z's that you see here, right, they're not multiplying, they're just saying that torque can be a function of that, j can be a function of that, g can be a function of that, of z, all right, as you go along it. And so the basic formula, like we have, Pli, PL over EA, or FL, or Fli, FL over EA. The analogous equation is TL over JG. Okay, you don't need to know for Tuesday, but you will need to know for the next exam. All right, and sometimes people are like, hey, wait a second, what's all this spring constant business or spring coefficient business? When did you tell us that shafts are also springs? This is the moment. Shafts can also be modeled as springs. Okay? And we might have, there might have been we probably didn't talk about it that much at the beginning, right? But just like we have our K's, right? And we've said for axial loading, K is equal to EA over L. Definitely know that for Tuesday, right? Or this, definitely know that for Tuesday. And unless you you don't want to be rederiving this stuff in the middle of the exam, okay? And then we have the same kind of idea, right? So torque equals K, some spring constant, K times phi. and this comes out to be JG over L. Okay? Any questions? All right. This is, of course, assuming a bunch of things, that this is a cylinder that is got a constant cross-sectional area, and the torque is the same throughout the region. What do I mean by that? Okay, just like, we have to think when we start using these equations, right, like this one, or this one, right? This is an internal torque. This is an internal force. These are forces, like if I take the slice and I say, okay, what's the internal force, right? And what's the internal torque? I can figure that out. And then if it's constant, that just means that, I got PL over EA and I've got TL over JG, okay, like here. If the torque is not constant, right? If it's like a distributed torque, just like if it's a distributed force, externally acting on the thing, right? Which means internally it's also not constant. I've got to think about the internal torque and how it's changing. All right, and that we cover. I'm going to jump over some stuff because it's important. Okay? So, if you have a distributed torque on a shaft like this, right? This is just like the distributed force, right? Or gravity acting, right? We've done this now. And we have like a rho GA, okay, you remember that? The units are a little weird first. So this is torque divided by length, just like we had, newtons or force divided by meters when we had a distributed force. So we have Newton meters divided by meters. So it actually means that, if you do this out, that your distributed torque ends up being just units of newtons. Okay? It's a little bit weird. And then if you're looking at how this works out, okay? If I've got this torque, all right, and if it's, if it's a constant here, distributed torque, I should say, then it's this TL, okay? If the distributed torque is not a constant, then you have to integrate this, and that's going to have some interesting dependence on, still on T and it's going to have, you're going to have to, so if the T is not a constant, right, then it's going to have some dependence on Z, and you're going to integrate with respect to Z. Okay? And what we do is we apply the angle of twist equation to the internal torque, okay? And that internal torque has to be calculated out. So often, just like we do in axial loading problems, we first do external equilibrium, okay? And then we do internal equilibrium, okay? And it's going to be a function of this distributed torque, T, lowercase t. And then we can integrate, but see now this is a function of Z, and so when you do this integral, you have to integrate appropriately, okay? And you've got these terms, and so it's just not like, remember if this was just a constant big T, right? Then it was TO over JG. This is a distributed torque, all right? That's running along the thing, meaning that the internal torque is not a constant as a function of Z, and so you have to do this integral out, and you get this equation as the result. Okay? Any questions? All right. There is some dicey stuff in these problems. These were kind of cruel, I think. This one on a previous exam. This one wasn't as cruel, okay? But nonetheless, they're a little bit tricky, and you can look at the previous exams if you get stuck. What I want to say here is there are two conditions that need to be resolved if you have gears, okay? geometric compatibility and equilibrium. All right, so you're like, okay, surprise, surprise. But what does that mean? What does that mean? It means if I have two gears that are mated with each other, okay, or like touching each other like this, and they have different diameters, okay? If I look at one gear and I roll it on the ground, and I go one revolution, it's going to go a certain distance, right? What is that distance? One revolution. Huh? It's the circumference, right? It's the perimeter, it's the circumference of that circle, right? If I take another one and I roll it one revolution, again, it's the circumference. They're touching each other. All right? And so, if I, how do you put it? If I take both of these gears apart and I roll them, right, one revolution, they're going to go different distances. Okay. And if I've got a bike, right, with two sprockets and they're different radii, I go one revolution on the big gear in the front. How many revolutions am I going to get in the back gear? More or less? Huh? Yeah, the back one's typically smaller, right? So if I go one revolution on the big sprocket, I get more, right, on the smaller one in the back, right? And I can go up and down, right, in my gears. I can go lower or higher to change that ratio for my legs. This is how car transmission works too, right? So the compatibility that we're worried about, geometric compatibility here, is that these distances, the distances, all right, they're going to go the same amount of distance in this case, all right, which is maybe a little bit counterintuitive, all right, but if, like they are tracking with each other, okay, but one may have to go more revolutions to go that same amount of distance, okay. So we look at the distance they have to go, and we get a ratio, all right, between the radii. And that ratio, you could think of, okay, phi 1 is equal to r2 over r1 times phi 2. So that's the first condition we have to satisfy. The second condition, right, we said is equilibrium. So for the second condition, what we're going to satisfy is, keep going. All right, so we satisfy geometric compatibility. Okay. The second condition is not equilibrium of torques. Okay? It's actually equilibrium of forces. So if I've got just two wheels rolling against each other, okay, I've got a contact force between these two wheels. Okay, so I have to satisfy my geometric compatibility over here, but I also have to satisfy the force at that point. Okay, they're going to be the same force, right? Equal and opposite forces. So I've got if I'm turning the bottom one this direction, okay, counterclockwise, then this gear is pushing on this surface in the left direction with friction. Okay? And if I'm using gears with teeth, as these teeth make contact with each other, it's the same deal. It's essentially a point force, or close to a point force, that's acting on one gear, or acting from one gear on the other gear. Okay, so these forces line up. F1 is equal to F2. Torque T here is not necessarily equal to torque 2. Okay? I mean, if they're the same radii, then okay, we're fine. But it's the forces that balance out here. Okay, so when you do this out, you get a ratio, okay, between them. So that, again, right, we said, all right, we have phi 1 is equal to r2 over r1 phi 2. In this case, it's torque 2 is equal to r2 over r1 times t. And in that also, you can probably remember that a little bit with your gear transmissions and your bike, right? You go into a lower gear. Why? To reduce the number of revolutions you have for a given revolution of your feet or the motor, right? You go into that lower gear, and what do you get as a benefit? You get torque, okay? So that's why you go into lower gears, so you get more torques, right? That's why a pickup truck is going to be geared for, it can be a huge engine, right? But you get a little Corvette or something on the freeway, and even though the pickup truck has a bigger engine, I mean, it's not always apples to apples, but you're gonna bank on the Corvette beating this other huge or semi or whatever it is, okay? In a speed game. But if it was a pooling game, right, you're gonna go with the pickup, or you're gonna go with the semi. Okay, so another way to kind of think of these things also at times, and that's not here, okay? This is not this question, all right? This is a nice static problem. But often if you have a transmission that's running at a constant velocity, we assume power is conserved. So that's another trick you can use, okay? Through a transmission, we assume you're like, what? Yeah, so gear transmissions can actually be extremely efficient, okay? And so you can assume that you have power conserved from one end to the other. And so where does power? Power is torque times angular velocity. Remember that from way back when, at the beginning? So that's another kind of shortcut way to go, okay, well, I know that my motor is producing this much torque and is spinning at this speed. If I have this much torque on the output end, then I know how fast it's running. Okay, what its angular velocity is. All right, and then for more out of order fun, we have indeterminate systems. This is the session that this keeps on giving. Okay, what does an indeterminate system look like? Well, remember what an indeterminate system looked like for axial loading? You couldn't solve for the forces. You couldn't solve for the displacements without looking at the continuity relationship, or looking at displacement force relationships. We can't figure out what the reaction forces would be without looking at torque angular displacement relationships. We have to use both, right? We've got too many constraints. If this were unconstrained, you can think of it, right? If I were to get rid of this wall constraint, and this is a perfect wall constraint, and I put a torque anywhere along here, I can calculate what's going on just by using equilibrium. But if I add another extra constraint, I have to think about equilibrium and constitutive relationships. Okay. All right, and I'll let you go through that. And then finally, the last thing is more pre-po-max. Okay, so, hey, you were so excited. All right, so, okay, what do we learn? You guys showed me some new ways to get pre-po-max to act up weirdly, okay? That was great. I'm sorry, though. Okay, so just a couple of things, completely unrelated to the mechanics. If pre-po-max is like not meshing, go into your task manager and make sure you completely shut it off, okay? And then try again. Just the meshing, right? Meshing doesn't take that long. That's like 4 steps, okay? If it's like spits out some weird error for meshing, just make sure you've got all the instances of pre-po-max gone. If that still doesn't work, delete the folder and download it again. I don't know how, all right? But those are like, you've heard the joke, right? Maybe you haven't heard this joke. I'm leading too much. All right, so a car is stopped on the end of the road, at the side of the road, right? And you've got a mechanical engineer, an electrical engineer, and a computer engineer. All right? The mechanical engineer, he gets out, he opens the hood, he checks the engine, checks the fluids, he doesn't check the battery, that's the electrical engineer, right? And he still can't get it to start, right? He just I don't know what's wrong. The electrical engineer, right? He goes, he checks the battery, checks the wiring, he still can't figure it out. He still can't get it to start, right? What does the computer engineer do? Huh? Yeah, the computer engineer gets out, opening the door, gets back in, closes the door, and tries to restart it. And it starts right up. Okay? So sometimes, right, it's not going to solve all our problems, but if you're having issues that don't seem to be because, steps or something, try restarting it. But I think generally, there were only, I think, a few cases where there are issues of that nature. Okay? Here's a biggie, though. Okay? Remember how I said at the beginning, oh yeah, you can do like epsilon 1, 1, that's equal to epsilon xx, right? And that's everyone's happy. That's true for their normal strains. But because of some of the tensor math, okay, that we won't cover in this class, to keep things straight for the transformations that have to happen, the epsilons, the E1, the shear epsilons that you see in pre-po max, the shear strains, like epsilon xy, epsilon yx, or actually in pre-po max, epsilon 1, 2, or epsilon 2, 1, those end up being half of our shear strains, of the actual shear strains. Okay? This is a math. So when I say, or if the question asks, hey, what is the shear strain? What's the shear strain xy? Pre-po max is going to spit out twice what it should be. So spit out half of what it should be. Okay? Thank you for making the face. I knew I did something wrong as soon as you made that face. So, if it's like, 0.2 degrees or something, all right, that pre-po max says, okay, it's really 0.4 degrees. Okay, just keep that in mind. Okay, so that's something, it's not true for the normal strains. It's only true for the shear strains. All right, on that, let's get to it. Any questions now about technical content or what we're doing? Okay. How much time do we have? We've got a lot of time. We got 40 minutes. All right. So, we'll go ahead and we'll, I guess, do this part of the thing.
The formula sheet, one side,
Two sides.
two side, one page.
Yeah, two side, one page. Yeah. Okay. Go back. All right, let's. Okay. Oh. All right. Okay, so there was a question.
No, because if we have complex that's
It depends. So here you're going to be looking at the face, right? And usually
Good job.
vector coming out of the face. So this one would be crosses. But if you're doing external bounds, it doesn't matter. So you just pick one of the faces. Right? Because first we do external torque, and then we look at the internal torque. So when we look at the internal torque section, we look at the face.
so like if it was negative, with the angle of this, we put the answer at magnitude or do
So it depends. I think we'll be pretty clear. We'll say clockwise or counterclockwise. Or, but yeah, but yeah, that's a good question.
also put this side, we just put
If it's a yes. Yes.
Okay, so for the exam, what are the sections between again?
Sessions 1 through 9. Not what we covered today.
Oh, okay, cool. And then also, Tuesday, where I was trying to do the pre-pro max, I was really focused on that. I didn't get to the attendance.
Okay, so send me a message. I remember.
Yeah. Okay.
Okay, send me in Canvas. Send me a message. Okay. All right, so there was a question on this problem. All right. There are two ways to do it. Do you guys want to do it with geometric compatibility? Do you want to do it with geometric compatibility or superposition first? Geometric compatibility. Okay, so Sue, you want superposition? Okay. Well, we're going to do geometric compatibility first, and then we'll do superposition. Boo. Okay. All right. Okay, so we have a pair of bars with properties, right? And there's no force acting in the middle. Okay? So if there's no force acting in the middle, what does that say about the force throughout the system? External forces, internal forces. It would be 0 if it was unconstrained. We're doing geometric compatibility, so we haven't released the constraints. Okay, so yeah, there's going to be one force, and it's going to be the same. All right, because there's no force here. All right, and with geometric compatibility, what we're looking at is making sure that the displacements all line up in the universe. Okay, what does that mean? That means that in this particular case, the expansion of AB, this region, plus the expansion of BC has to be equal the expansion between C and A. Okay, that's right here, geometric compatibility. All right, now, practically speaking, okay, what do we know about the displacement of C relative to A? What is delta C slash A? Any participation? 0, thank you. It's 0, right? Those walls are walls that do not move relative to each other. Okay? So this displacement C over A has to be 0. That's this. And that means that these two, when they add to each other, equal 0, which means that if the BA goes to the right 1 millimeter, then BC is going to have to contract by 1 millimeter. All right, so we've got geometric compatibility. We've got some constitutive equations we can write. Okay, we know that we can think of these bars as being springs. So generally, right, we have a K1 over here, and we have a K2 over here. K1 would be E1A over L1, and K2 would be E2A over L2, right? And we also have a relationship for linear expansion. Okay. Alpha delta T times L will give us displacement, or if we're looking at strain, it would just be alpha delta T. Okay? So we've set up the problem. Equilibrium, geometric compatibility, constitutive equations. These 3 pillars for attacking a problem that actually they come from Crandall, Dahl, and Lardner, if you look at the videos that we put up. Okay? Well, what do? The key thing to think about a little bit here is what are delta BA and delta CB. And this takes a little bit of thinking. Okay? And they're like, oh, you told me I wasn't going to use superposition. Well, we're not using superposition of forces here, but we're still thinking about how the displacements are due from force and how the displacements due to thermal expansion are going to add up. Okay? So in this case, if I had, if it were unconstrained, right? If it were unconstrained and F was equal to 0, then I would just say, okay, well, delta BA is going to be alpha 1 delta T L1, right? Because that would just be the unconstrained expansion. And if I look at CB, right, this region, same thing, alpha 2 delta T L2. But that's not what we have, right? We have a force that's pushing this whole thing together. And that force is counteracting this thermal strain, or this thermal displacement, or thermal deformation, better said. Okay. So now we look at delta B relative to A, and we say, oh, well, guess what? I can handle this if I also think about the internal force, right? If I take a slice here and I think about the internal force, that's the same as the constraining forces at the walls acting on the system. And both of these elements, everything is going to be in compression. Both of these regions are going to be in compression. Okay? So they're going against each other. All right? And so I've got this relationship. K1, like we said, E1A over L1, right? So this is kind of taking from the constitutive relationships. K2, E2A over L2. Okay, great. Geometric compatibility. These two, I add them together, they've got to be equal to 0. So I use geometric compatibility. I've already used equilibrium, okay? Because I'm thinking about what the forces are happening here. And then I put all these things together, and I just solve for F. F is the only unknown. I know alpha 1, they tell me the temperature change. I know L1, F, I don't know K1, I can calculate it out because I know E1, A, and L1. So I just solve for F, and this is what you get. Okay, now, that doesn't do everything, right? Because so now I've got my force, but they wanted to know how much to the right this thing is going to move. Right? So what do I have to do? Well, the simplest way, if I'm just interested in how this is going to move to the right, I just say, well, I got to pick either the delta B relative to A or the delta C relative to B. Right? Then they're additive inverses of each other. So if I plug in F back into here, I can get my delta B relative to A, and that's how much this is going to move to the right. Okay? So that's it. Yes. Excuse me? This is what I would consider to be using geometric compatibility. Okay? I mean, there is a sense of superposition because we're looking at the displacements. Okay? When I think of superposition for these types of problems, I think of removing a wall.
I mean, isn't that what you did? You let it expand. That's where it's
Yeah, I think of removing a wall and then applying a force to get that displacement back. The total displacement back. Okay? So for example, for here, all right, what we do if we're going to use the method of superposition, we have this indeterminate system, right, that's been over-constrained. And then I release this wall, I get rid of it, and then I have the overall displacement, which is going to be delta 1 plus delta 2. And so you're saying, oh, well, isn't that geometric compatibility? Yes, but I release the constraint, and then I'm going to add the constraint. That's usually what happens in superposition. Were we using superposition before? Okay, sure, you could call it that. All right, for the displacements when we're calculating the delta B relative to A and the delta C over B. But you'll see that this process is pretty distinct. So we're using superposition. We have some interesting things happening with geometry, and we still have the same constitutive relationships, except now we're going to think about the effective spring constant of the entire structure, of the two combined. So that's going to have an effective spring constant of K1, K2 over K1 plus K2. All right, that's what we see here. Again, internal forces are going to be the same, all right? And these are unconstrained values for displacement and thermal strain. Well, what do? We say, well, if it's unconstrained, I've got a delta, which is just the alpha 1 delta T1 plus the alpha 2 delta TL2. Okay. And that delta, all right, has to be what I apply enough force to swish it back to its original length. So I can calculate out what that force is by using the effective spring constant with that displacement or with that expansion. And so now I know what the forces on the walls are, and they're going to be equal to F1, F2. F1, F2, really, you could think of them as internal forces now. Okay? And they're the same. They're all the same, like we said before. Okay. This is where it gets a little bit, I think, a little bit tricky. So we're going to apply external force, right, to the constraint of displacement, and we can come up with these delta 1F and delta 2F, right? And this is kind of like what we did before, right? Where we were looking at the geometric compatibility version, where we were saying, okay, I know I have some displacement due to force, okay, and that's what we're calculating now. Okay, and I can think of I've got strain that is due to force, okay, because if I divide by L1. And we can think of the strain or the displacement as kind of, in each of these, as being a combination of the thermal strain and the force-based strain, okay, for both of these. Okay. So this is a strain in the first one, this is a strain in the second one. Okay, so what do we do with this mess? Well, we can say that we have strain due to force as just F over EA. We have a strain, a thermal strain, which is alpha 1 delta T. All right? And we can write out what the strain due to force is just because we know what the force is. All right? Right? This is F over EA, right? Okay. And this was the force, K1, if we go back, right, over, it's actually right here. This is the force, right? So this is F over EA, and the same thing applies here. F over EA, but now it's a ratio of the elastic moduli. Okay. And they're negative, because they're both in compression. So now, what we can say is that the strain, the overall strain in the first region is equal to the strain from force, which is a negative, plus the thermal strain, okay, which is alpha 1 delta T. And this gives us epsilon 1, okay, for both, or for the left side. And this gives us epsilon 2. We only need one of these expressions. Epsilon 1 times the original length, L1, will then give us the displacement to the right. Okay. All right. Thank you. I hope that helped clarify that question. So let me just walk around now, okay? Because that one's a big one I thought people would want to ask. Other questions? Other questions? Okay, I'll start gonna move up. All right. There's just there, but it's not.
That was today, wasn't it? Oh, Saturday. That's the general design. But I'm not. Well, we have the exams.
Okay. So, yeah. So, okay. So, this is how I do it. Okay. So, I think you that are listening to how you say what it means that getting into the details of what that external force and getting the data really, I think it's really hard. So the way I look at this zero displacement. Okay, that's how I would do it. And that's how I did do it. Okay. There's some interesting things. One. You realize that this bottom right? So whatever is displacement there, so then you can comment what's the displacement there. So the displacement in the operation is a result of all these forces. So whatever all these forces increase to, that's not. Okay? So that's going to be the lower here, or the axis TV is distributed here. That's how I call it. So it's going to be T times L2. Right? T times L2 and then times L1 very big. Okay. That doesn't come with that displacement. That's the displacement 16. Then you got to figure out the displacement that is more, right? That is the CV L2 over JD. Alright. So that one you figure out. So now I figured out all the displacements. Figure out here, and I add them together. And now I need to go how much force I need to take. What's that? That's not that hard because when I put this back, I'm not including this. So it's just whatever that force, that displacement to be, whatever the constraint force is, times 1 L1 Okay, and so that, I don't know if you're following. That's how you figure out. And now I can figure out and put the okay, so then now I know the internal torque is here, whatever that returning torque is. And that's I mean then that
Let me see if this works now.
Does that make sense? I don't know what the profile is. Okay, give that a shot to figure out what works. Yeah, I think it's going to rotate that. Right. So, and I'll give you I think actually you teach this one pretty straight. I'm just asking for yes. Which one? Oh, yeah. Okay. This is harder than right. So I just took a picture of that.
I'll let you know. They want to join in. I think he's also stressing about this guy.
Yeah, I think it's not going to be about the right. So I would do like a 3, right? Where you have to say, okay, I got B on the left, I got shoot on the right. Okay? And which way I'm going to say B? Well, the way the force would be 5 and 2 times A2, right? Try to be right, and that one, this one goes this way, this one goes that way. Both lines go. Well, no, the angles don't get added, right? So we even out that really, everything has to balance out. Okay? So now, right, the force is in the balance. Okay? So this,
The whole thing's square.
you have a force, right? So the amount that is like, some balance. And this is a little bit tricky because you've got an external force acting on both of these, right? But then you have to, you essentially have a force, right? At a radius as well. Interacting. So the force, how do I say this? The force is being balanced out. Right? The force is being balanced out for the So there's a force, so if we just draw out the two circles, right? Yeah, I've got a force that's on the near that I would draw this way. Right? And I'm gonna say that force is 10 to G times 8. Okay, right? So that's that force. But I also have a force on that thing, right? That's pushing up. Okay? And then on the right here, I've got a force pushing down on it. Okay? And I've got a force that's pushing clockwise, which is M1A1 or M1G1A1. So write it out. So the radius the force is at the mouth. Yes, so that will work out right. You're right. The length of it. Yeah, so write it out. Yes.
I didn't want to.
Yeah, I can't go through. Yeah. If you have questions about that, I'll start with mine. And I have all stuff on my as well. Right. Yeah, I can't, so I mean, I'd say, yeah, I can't go through everything. Alright, but, this is just something. Yeah. It's not, I mean, it's not, you know, we can say just, but it's very tricky, right? And I would start with the more recent exams, which are more moderate, a lot more tempered than the earlier ones. Don't start the other direction. Okay? There's 2015 and 2016 and a little bit creative. I think there's someone back here. I gotta go out and come back. I'll be right back. Okay, yeah, you can go. Okay. Yes. Okay, and I wanna say, yeah. And I wanna say, okay, never thought. Okay, so like, that one was gonna be a little bit of stress. Okay, what's up? Yeah. Okay, that was mostly to explain the concept of what it is. Okay, but yeah, we're not gonna yes, yeah. you know.
Like, we know from
And
the
then we'll hold on
baseline.
to the-
Oh, so that's what you did. Okay, I thought you did like something like that.
Yeah, we.
Yeah.
And, right, because sometimes we have. I think those are all fair games. They're all fair games. I wouldn't go through the, like, math, sorry.
Yeah, you have to find the derivative.
And then realize that. Like, we're doing, like, math. Right, and even like. Angle. So. And then we have. Which actually is.
Some curves are gonna be decreasing and some curves are gonna be increasing based on the
Okay, hold on, yes. Paul had a question on that. Okay, all right.
And then he said,
Now there are like three of you back.
but I don't see why he thought it.
Yeah,
Because it looks like it's
okay, I'll ask, okay, so. What do you mean, look what to look for?
Like, I didn't mean to draw it like that. So like upper minus 2 is an increase in.
We have to think a little bit here. We have,
Like, I like messed up, but now I know not to.
and, okay, this is a good one. So, we can see now, are we on the top, the bottom, left, right, where are we? And it turns out they're all going to be, they're gonna be, the same, right, because of the circle. If we're on the top, we're looking at an element. Okay, so remember Z is this way. Okay, and I'm looking at an element on the top. And the way to define things, Z is this way. Okay, and I've got an X cross Y, right? So X would be like this way, Y would be up. Right? So if I'm looking at the shear of that top element, depending on which way you define the torque, okay? Let's say we define the torque in a positive Z. So then that means that this side of the element is going down, this side of the element is going up, okay? And this element, if I'm looking down, I'm on the Z face, right? I'm on the Z face, and I'm in the, remember what we just said? We said that we have, we have the Z this way, I'm in the negative X direction. Okay, so it's that would be a gamma Z X, right? Z face X direction. That would be the negative number. Okay. And ZX, that corresponds to E3, or E31, right? Or E13. They're going to be the same, right? So that's what we all saw. And you should have calculated it out before, right?
What if it is not small?
So it's a shear stress. I think I like to think of shear stress as shear strain, right? And I'm thinking about what is the box? What is my square that's being twisted? What is it doing? It's radially going around, so Z is what, it depends, actually, is yours defined, how do you define it? X is coming out of the face? Okay, well then it's different, so X is coming out of the face, then you might have a Y coming out and Z is coming toward you, right? Okay, so in that case, it's gonna be an X face, alright, and the stress is, or the shear stress is gonna be in a Z direction. So it's still a 1, 3, right? 3, 1, 1, 3 is still. That helps? Okay. All right.
This is right.
Yes. Yes. Yeah. Why is your waitress? Yeah, so, what are you applying it to? The risk in the courts? Yes. Yeah. Well, it's how it works out. This is 4, because, you have equilibrium of forces, the contact force, right? Between them, and you have the geometric compatibility, the R1, I1 to R2, 5. And when you do it all out, yeah. Remember we said the forces are not going to be equal to each other. No, so they have to both factor in. If you're going to look at the relationship between forces. So if you do it out, okay, so there's multiple ways to the structure, but yes. No, don't use, so yes, often with power, that's how it works out, right? This one is this. This is. This one.
Yeah, and we're gonna have like.
Which problem is it? Which problem? Okay, you're doing it. Okay, which problem is the graph? Yeah, okay, so, okay, good. Yeah, this is the multiple parts, okay? So, if you're looking at, the relationship between the mass, okay, these have R's and A's, if you're looking at, because I don't think it even solved for the course the way I did it. Yeah, so there's an R squared ratio. Yeah, I got it. Yeah. Okay. Because, like here, right, this is the ratio of the displacements, right? And then we have the equilibrium of the forces, right?
There's a lot more to it, but that's
I'm gonna try to answer another question though. Actually, this is not, wait. No, because this is angle twist, so we have. Yes. Yes, there was a, you had a question on, what time is it? 7. Oh my goodness. Okay, do you want me to go briefly through, who were asking about the, the elephant question. Okay, and what's your question?
About the angle of twist, so we got a really small number and like that's the correct formula.
Mm-hmm.
And yeah, our limits are that like very small.
Okay, well, so that's just in a read, right? Okay, so that one. Right, okay, it is, yes, it's list of shaft AU, okay? Yeah, that's not, the next one is from A to B, yes. Yeah, so you're okay. I don't remember the numbers, to be honest. Okay, this whole thing, Oh, we didn't do like that. Okay, so I'm thinking like, this is gradient. Right, so this is maybe 7.55. Maybe here. So these angles are going to be gradient. In order to get these degrees, you have to. Maybe part of this. Yeah, it's gonna be small. Why is it? Oh, where did that go? That's 10:09. That should be 10:09. We're getting closer. It is gonna be small, but it's not that small. No, it's 10:09. Okay. Good, I'm glad.
Professor,
Yes.
can we ask a quick question?
Okay, what's that?
It's about angle twist.
Yes.
It's about what's this thing called,
Indeterminate?
It's just the question is like, so it's the hole that's fixed that we can fix it.
Yeah, so that people want, that's the one that people want me to go over, so let's talk about that. Oop. All right, so. Which number is it? Okay, I'm in the wrong session. This one?
Yes.
Okay. All right. So the way I would approach this and the way I did approach it is to think about trying to figure out what the internal torque is in this member BA. You guys can't see. Is that too small? It's okay? Okay, figure out what the torque is in this member BA. And in order to do that, I'm going to use superposition. Okay, well first, if I figure out what the torque is in here, right? You agree that I can then calculate phi BA, right? Because it's just going to be that torque times L3 over JG, right? Okay, so in order to figure out what that internal torque is here, I got to figure out what the reaction torque is at A. Right? If I know the torque at A, I can take a slice and then I can say that internally that's got to be the same thing or opposite of what's happening at this bottom constraint. Okay? So that's the simple part, but it's the kind of overarching goal that we're going for. The hard part, of course, is to figure out what is that reaction torque. So the way I suggest doing it is using superposition, where we're going to unconstrain the bottom. Figure out what the displacement is of this bottom piece, right? What phi A to D is when it's unconstrained. And then I'm going to apply a torque that gets us to 0, right? So that it gives us that same amount of displacement. Right? And that'll be the torque. So the torque that goes against this displacement, to be clear, that torque is actually not that complicated in terms of the angle of displacement, because that is a rod that has length L1, L2, L3. I'm ignoring this distributed load, right? And I've got some torque, and I've got some huge length, L1 plus L2 plus L3 over JG. Okay, I probably went too fast there. So let's go a little bit slower. What I'm suggesting is that this problem can be modeled as this problem plus this problem. Okay. This is unconstrained. Phi dA, we'll call it just from this load. Okay, unconstrained. And this is some reaction torque, okay, being applied at the unconstrained side to get these two displacements, angular displacements, to be the same. Yes? Yeah. So I add this one plus this one and I get 0. These are additive inverses of each other. Or they're the same, actually they're in opposite directions, so they're actually equal to each other. The displacements are. Okay? This is using superposition. All right, I'm going to make them be this way. I'm going to apply sufficient torque such that it does end up equaling what I got in the displacement. So I need to calculate out this one first, so then I can plug this one into this one. Okay? Does that make sense? Everyone, am I making sense up to this point? Okay, so how do I calculate this unconstrained problem? You tell me. What's that? Well, kind of, but not really. Let's look at it. All right. So, what's the internal torque in this region here? This upper region. Or, well, it's kind of flipped now. But this BA region, what's the internal torque there? In this region, it's flipped. If this is unconstrained, what's the internal torque in this portion that's closer to the unconstrained end? 0. Yeah, it's 0. Okay. What's the internal torque in this region that's close to the constraining wall? What's this torque? T, yes, and what is T? We just learned this, so it's a little bit tricky, okay? in this region, okay, the torque that it's going to be experiencing is from this distributed torque. Okay? This distributed torque, all of it is acting over this length. So the total torque is the integral of this distributed torque times, or within this length. So it actually just ends up being TD times, I guess this is L2. Okay, so that's the internal torque here, TD-L2. So I can figure out what the angular displacement from here to here is, okay, if I with this torque. That's just going to be TD-L2 times, I don't know if this is L3 or L1. What is it? L3. So that's TD-L2 times L3 all over JG. Okay, so that gives us the angular displacement B of, wait, hold on. Whoa, no. It's actually L1. It's the TD, because yeah. Well, it's L3, yeah, okay, that's fine. I unconstrain the top. I guess I unconstrain the top, all right? And then the trickiest one is, what is the displacement of the middle region? And that one I just explained too. That one comes from this equation, right? I think of, hey, what's the middle twisting by? It's twisting TL squared over 2JG. Okay? So the angle, it depends on which side you unconstrain. I'm sorry for that confusion, right? But essentially, you have the angle of twist on the region closest to the wall. You have the angle of twist on that middle region due to the distributed torque. And then you have that other region that's just along for the ride. Because there's no internal torque, so whatever the displacement is of those two, that just follows through. Okay? Keep it real. Okay? So now I figured out, I add those together, and I've got the angular displacement of the unconstrained state. So now I have to apply a torque that gets the entire bar to have the same displacement in the opposite direction. Okay, because then remember I had to add those two displacements so that they equal 0. So that comes in, so this is a react. So this is what we're calling the displacement due to the loading, okay, but it's unconstrained. The displacement from the reaction wall, okay, I don't know what the torque is, but that torque times L1 plus L2 plus L3 all over JG, that's like putting all three of those in series with each other. Okay? And so that entire length, because there's no distributed load in that case, that was in the unconstrained side. On the other part, that came over here, okay, from the load side. This is the reaction side. So this whole thing is going to be describing the angular displacement of the entire rod with L1, L2, L3 is the length. And these two, when you equate them to each other, the only unknown is the reaction torque. That reaction torque that we wanted from the wall acting on the system. Okay? And once I know that reaction torque, then I can say, plug that into, I can plug that into just that little length, that AB length that I want. All right, and I can figure out what the displacement is there. Okay? Does that make sense? More or less? Kind of?
I mean, now I have more of an idea how to approach it.
Okay. Yeah, it's a complicated problem. It's a complicated problem. And all this is available, if this is from, I think, the 2020 exam. Yeah, it's the same problem from the 2020 exam. All right. Okay, we got to pack up because I think they're having a meeting in here at 7:30. Yes, Paul.
When you mentioned about the pre-pro max about like half the number again,
Yes.
can you just say that one more time?
Yeah, so if you look here, pre-po max, okay, is going to give you like an epsilon 1, 2, epsilon 1, 3, whatever it is, all right? But what we really want is a gamma x z, okay? So this is going to be half of what this is, right? Yeah, because 2 times, right? So 2 times this will give you what you really want. Okay, when you look at the epsilon 1, 3 or epsilon 2, 3. Okay, good. Thank you, everybody.
Professor,
Yes.
I missed the